too hung up in kind of overthinking what's going on here. I don't need you to overthink. I need you to just watch. This takes quite a while to develop what's going on, and over the next couple of days, between 13.3 and 13.4, we're going to kind of gel all of this stuff together so that we can apply trigonometry to pretty much anything. Okay, it's pretty cool the way this works. So it says use angles in standard position. That's one of our goals. So we've talked about standard position already. We're going to talk about reference triangles and reference angles. So reference triangles and reference angles are super important, and there are people that just naturally, everybody, about probably half the people do them the wrong way naturally. You have to make sure that you're drawing the reference triangle and the reference angle the right way. If you draw it the wrong way, you are going to get the wrong answer and you're going to get frustrated, okay? So we're going to start with a little bit of simplification like we were just talking about. So here's the deal on this one. I want to rationalize 1 divided by radical 2. So we're going to multiply the top and bottom by radical 2. That's going to give me a radical 2 on the top. I get a radical 4 on the bottom. If I wanted to, I could write it radical 2 squared. Either way, the two of those undo each other, which is the entire point. I want something that has a nice denominator. When we say rationalize the denominator, basically we just want a nice denominator, okay? We don't want something that's ugly to work with. Denominators and fractions are hard enough to work with without having ugly numbers. So here's the answer on this one. I'm going to go ahead and circle this one. We do the same type of thing here. We're going to rationalize the denominator because I need a pair of 3's in order to take those out. So I get a 3 right here. I get a radical 3 on the top, and that's the answer. Now, when we get to this point, and again, just to make sure everybody's clear on this, my gosh, it looks like you ought to be able to cancel the 2's and the 2's and the 3's and the 3's. Can you? Somebody raise their hand and tell us why not. Zach.
Radical 2 is not the same number as 2.
Very good. That is not really a 2. If you throw it in your calculator, you're going to get something around 1.41. And that's not really a 3 either. So when those numbers are underneath radicals, they are not the same number. Okay? So we can't just start canceling those and stuff like that. So would somebody raise their hand and tell us, how am I going to rationalize the last one? Because there are lots of different approaches to this. I like the easiest approach. I hope somebody's going to suggest the easiest approach. Luke's had his hand up for a while. We got a couple other hands up. Luke, what do you think? That's all you need. The 2 shouldn't bother anybody. There's nothing wrong with having a 2 on the bottom, so we're going to multiply by radical 5 on the top and bottom. So this is going to give us a 3 radical 5 on the top. And on the bottom, I have a radical 5 times a radical 5, so that's a 5. Still got the 2, so we end up with a 10 there. And that's the answer right there. And then, of course, we beg the question, can't I cancel the 5 with the 10? No, because it's not really a 5. If you type radical 5 into your calculator, it's going to give you something around 2.2, but it is certainly not a 5. Wilson.
So say you had like radical 8 on the bottom. Could you times it by radical 2 to rationalize it?
You could, yes. He's got a great question here. Thank you very much. This doesn't derail the conversation at all. This is right on topic. Here's his question. What if I had 1 over radical 8? Remember, what we need is we need pairs of factors. An 8 is 3 2's. I've already got a pair. I need 1 more pair. So when you rationalize denominators, the problem is about getting enough of what you need. We need another 2, so if you wanted to do radical 2 here and radical 2 here, that would work just fine. Excellent question. Zach?
This is kind of random, but since they're radicals, could you square both?
No, that would be like saying, hey, I can just take any random number and I can square it. If it was an equation, you could square both sides, and then maybe that would be more useful. But when it's a number, you can't just randomly do stuff to it that you want to do, okay? You've got to be fair. What we've done here is we've been fair to the top and bottom. If you think about it, what we've done is we've multiplied by a conversion factor. Radical 3 over radical 3 is another type of conversion factor. We've made it look like we want it to, okay? Excellent question, though. I'm sure somebody else had that. So a couple of things we want to be aware of. Notice that this is in the I can statement for today. We're talking about angles and standard position. So standard position is when we have something like this. Its vertex is at the origin, and then a new vocab word here. Its initial side is on the positive side of the x-axis, and the terminal side is rotated to create the angle. So here we go, right here. This is the initial side. and this is the terminal side. Oops, let me make that look right. Terminal. Okay? Now, when we rotate this, generally speaking, we make positive angles by rotating it counterclockwise. That keeps us in quadrant 1. We're going to try to not overly complicate things. We're going to keep a lot of things in quadrant 1 for right now. Okay? Then I'll show you what happens when we rotate things into quadrant 2 and so forth. Okay, so here's the deal on this little picture right here. The vertex is at the origin, just like we said. The initial side, the starting side, is on the positive side of the x-axis, and what I've done is I've kind of swung this terminal side open to expose this angle right here. So you'll notice that that angle looks a little bit different. That is the Greek letter theta. We often use Greek letters to represent angles. The most common one is theta, alpha, beta, and then gamma. Gamma looks pretty funny, okay? So we use those to represent angles. And as we've seen before, angles in standard position are not limited to the acute angles in quadrant 1. So this is quadrant 1 right here. And again, if you're not familiar with this, make sure that you've got it. Quadrant 2 is right here, quadrant 3 is right there, and quadrant 4 is right there. So that takes us all the way around the circle. We've got all the quadrantal angles, 90, 180, 270, and then all the way around to 360. Everybody okay with that? Smart, we doing good? All right, so let's come down here and let's talk about what a reference triangle is and what a reference angle is. So we can draw a reference triangle to help us find the sides used in a trig ratio for an angle in standard position. So here's how it works. A reference triangle is a right triangle drawn in the correct quadrant, so right quadrant right here, using the x-axis as one of the legs. You have to use the x-axis as one of the legs. And we need to, the sides of the triangle must be correctly labeled with the correct lengths and the correct sign, S-I-G-N, which is one of the hazards when we start doing trigonometry. If I say the word sine now, you might go, wait a minute, are you talking plus or minus, or are you talking S-I-N-E? You're talking a trig function.
Just say sin.
What I'm talking about here, yeah, just say sin, I dare you. Okay? What we're talking about here is if we go left, we need a negative x coordinate. If we go down, we need a negative y coordinate. So that's what we're talking about there, and you're going to see that. Again, we won't dwell on that a whole bunch, but you'll see where that comes up. So here's a reference angle. A reference angle is a positive acute angle formed using the terminal side of an angle and the x-axis. Now, we are going to make a gigantic point of this because this is where about half the people go wrong because they've got an inclination to do this wrong. Nothing wrong with that. It's just like, hey, if I was a mathematician and I were inventing this, this is what I would have done. Well, it's not what they did and not what they decided on as far as a standard and conventional procedure. So here's the deal. Put a star by this. This is the note. Would you underline the word always? It's already bolded. I get that. We always make reference triangles and angles with the x-axis. So put x-axis right here. We never make reference triangles with the y-axis. If you were in charge of inventing this and coming up with conventional ways to do this a couple hundred years ago, you could have done whatever you want, but there are specific reasons why we make reference angles and reference triangles with the x-axis, never with the y-axis. Okay? And I'm hoping by what we did with circles in Unit 12, you kind of see the logic as to why we do it with the x-axis. So I'm going to slide down here. Here's example number 1, and it says this. Some details are important here. It says, given that alpha is in standard position in quadrant 1, find the reference angle theta and the missing trig function. So this is what we're going to do. They told us that it was in quadrant 1, so I'm going to draw a triangle in quadrant 1. I'm going to drop a line straight down to the x-axis, and I'm going to make a right angle right there. This is alpha. Alpha looks kind of like a little fishy shape with an open tail. And what it told us was that the sine of alpha was 4 over 5. So I'm just going to pick on somebody just at random, so you better be on your toes because at this point we've got to have these memorized. I'm going to pick on Caleb. Caleb, what two sides are involved in the sine ratio?
The hypotenuse and opposite.
It is the opposite. Which one goes on the top?
The opposite.
It is. It's the opposite. Caleb, how do you remember that? Just do, okay? Just do a little bit faster next time. Okay, so the opposite side is 4 and the hypotenuse is 5. Now, if you use the Pythagorean theorem, you can figure out what this one is right here. I'm hoping this looks familiar.
That one's like locked in my brain as 3.
It's a 3, 4, 5 right triangle. 3, 4, 5, it's a Pythagorean triple, so it's right there. Now, what I want you to take note of is this. We went to the right and we went up. So all of these are positive measurements. The hypotenuse is always going to be positive here. So what we want to do is we want to figure out, well, hey, if you said that the sine of alpha is 4/5, that means I can figure out alpha by doing a sine inverse. So grab your calculator. I'm going to be quiet for just a second, and I hope somebody is going to say something. I'm going to be quiet for just a second, and I'm hoping somebody is going to say something. Especially since you're using calculators that somebody else was using last period.
Oh my.
Oh.
Samara,
Change it to degree.
change it to degree mode. So grab your calculator, hit the mode button. You better come down here and, whoops, mode. Come down here, put it in degree mode, and then we're going to hit second quit, and then we're going to hit sine inverse of 4 divided by 5. Hit enter, and I got 53.13. Is that what you got?
Yes, sir.
Yeah.
Okay. Just, do you still have your chart, your trig table?
Yeah. Somewhere.
Do you
Yeah, I do.
want to have some fun?
Not really.
Oh, you don't?
Yes.
I'm okay.
Okay, good.
Come on.
That's point 8. Would you grab your trig table? I'm going to pull up a trig table right here. You want to find a sine ratio of 0.8. So look through there and find a sine ratio of 0.8.
What is it? He says.
First column here, right? Certainly not over there. They get bigger and bigger and bigger. We want one that says 0.8. 0.8 is about right here, 54. So a trig table can only give you that much accuracy. What did we come up with?
53.1.
We came up with 53.1. Oh, by the way, that's my house. I showed you the tree that fell over, didn't I?
No.
I didn't?
You hate our class.
No, I don't. I'll come back and I'll show you
Probably
the
didn't
tree that
because
fell over.
You had the teacher girl in here filming you.
The
and
teacher
you
girl,
wasn't
blah, blah,
talking
blah,
about
blah, blah.
yourself.
Okay, so 54. And what did we get right there? We got 53.1. So that was about as close as we could get. So that means alpha is 53.13 degrees. So we've got that part. And then it said, hey, would you figure out what the cosine of alpha is? So the cosine of alpha is 3/4. I'm going to put somebody on the spot. Mason, what two sides are involved in the cosine ratio?
Opposite over
Good try. Try again. Adjacent over hypotenuse. I'm going to put somebody else on the spot. D, what two sides are involved in the tangent ratio?
Opposite over adjacent.
So tell me what to write down here.
Is it going to be 4/3?
It is 4/3. So those are the 3 different parts of the answers on this problem. We figured out what alpha was.
Cosine should be 3/5.
Oh, it should be 3/5. Thank you. Thank you. Thanks for catching that. Thanks for catching that.
Cos.
Okay? All right, we good? Okay, let's turn our attention to the next one. Okay, this one again says, makes it nice for us, it's in quadrant 1, so I'm going to change colors here. This is the tangent ratio. I'm going to put Gavin on the spot. Gavin, tangent ratio, what two sides are involved?
Opposite over adjacent.
Okay, and then I'm going to put Colson on the spot. Colson, is that a ratio? Radical 5?
Yeah.
You sure?
Yeah.
How can you make it a ratio so everybody else knows it's a ratio? Put a 1 below it. Okay? And this is the opposite, and this is the adjacent.
What?
So we're going to draw a triangle. It said it was in quadrant 1, so we're going to make it look like this. This is alpha. Opposite is radical 5. The adjacent is 1. Legs squared plus legs squared equals hypotenuse squared. 1 squared plus radical 5 squared equals x squared. Wouldn't this just be 1 plus 5? Wouldn't that just be radical 6?
Yes, sir.
Perfect. Okay? Now, I'm going to write alpha equals tangent inverse of, don't hit enter. Tangent inverse of radical 5, right? Hold on. Big angle or small angle? Don't say anything. Big angle or small angle? Is alpha going to be a big angle or a small angle? And kind of the cutoff is 45 degrees. 45 degrees is halfway between 0 and 90. So is it bigger than 45 or less than 45, I guess is the question. How many say smaller? Okay, put them down. How many say bigger? Okay, put them down. Let's type it in. I just went over that. Oops. Bigger, right?
Yes.
Can somebody tell me why it's bigger? Lizzie.
Okay, so the adjacent side is 1, and then the opposite side, if radical 4 equals 2, and then radical 5 has to be bigger than 2.
Yeah, this side's more than twice as big as the adjacent side. So if the opposite side is bigger, we're going to expect a bigger angle. So the answer on this one is 65.91. So alpha on this one is 65.91 degrees. Okay, so we got that one. Now all we have to do is we just write down the sine of alpha, and we write down the cosine of alpha. Let me make sure I can do this without writing down any mistakes. Opposite, radical 5 over radical 6. Adjacent, 1 over radical 6. Am I doing okay?
Yeah.
Rationalize. Radical 30 over 6. That doesn't look very good, but that's the right way to write the answer. And we've had enough practice on this one. I'm hoping you can just write down what it is. Again, we're just going to multiply by radical 6 on the top and bottom. Radical 6 over 6. And as much as we would like to think that we can simplify some of those, we cannot simplify either of those. Okay, are there any questions there? We're good?
Yes.
Okay, all right. Back here, you don't need a calculator for this. So I'm going to slide down here, and this is where if you went through and you reviewed those ideas on special right triangles, you're going to be much better off. So if this is a 45, 45, 90, it's basically half a square. So if this side is x, this side is also an x. If I want to know what the hypotenuse is over here, I can say legs squared plus legs squared equals hypotenuse squared, which means I have 2x squareds equals c squared. So this is where Zach's question earlier, hey, can I just square both sides if I want to? Not unless it's an equation, not unless you're fair to both sides or fair to the top and bottom if it's a fraction. We're going to take the square root of both sides. So if I take the square root of both sides, and yes, I realize you've probably seen this before, this is what we get. We get the square root of 2x squared. We can take an x out because we've got a pair of x's. So we'd write this as radical 2 times x, or by convention, because we don't want anybody to confuse the fact where the x is, we normally write it like this. We normally write this as x radical 2. So on a 45, 45, 90, because that's half a square, these two are exactly the same, and to go from the leg to the hypotenuse, we times it by radical 2. Raise your hand if you've seen that before. Good. Okay, let's do this one. This has a 60 here and a 60 here, which means this is left with only 60 degrees here. We've dropped a line straight down, so this is 30 degrees on this side, right, or not at that angle right there. Dropping that altitude straight down on this equilateral triangle cuts this in half. That makes this x. If the whole thing used to be 2x, that means half of it would be x. Are we doing okay? What I don't have is I don't have this piece right here. So let's find that piece. Legs squared plus legs squared equals hypotenuse squared. And before I forget, you'll notice that what we're doing to solve these is we're using the Pythagorean theorem. So I have x squared plus y squared equals, this would be 4x squared. And this is where the 3 comes in. Dane's going to tell us how the 3 arrives into this little formula. How does the 3 show up? Dane's going to phone a friend. Wilson.
Because you gotta subtract x squared from the left.
Which gives us y squared equals 3x squared, and then we're going to pull the same trick we did over here. We're going to take the square root of both sides because I just want to know what y is. And then I'm going to write it by convention. I'm going to write the x out front, and I'm going to write the radical 3 right here. Okay? So these are the relationships on the special right triangles. Now what I want you to notice about this is this. Everything on a 30, 60, 90 has to go through the short leg. Notice we've got an x here, an x here, and an x here. Okay? So you've got to figure out what the short leg is before you find out what the other ones are. And then I also want you to notice this. Some people will get confused and they'll say, you know, I really have a hard time memorizing which is which. Okay? Yes, there's a lot of memorizing here and understanding. If you want to go back and derive this every time, you're welcome to. This is what I would do. 30, 60, 90. It's the only one that has a 3 in the name, and it's the only one that has a radical 3 in it. So 45, 45, 90, there's no 3 in that name. That one's got the radical 2. This one has the radical 3. Okay? So flip the page over. Hey, Ryan, will you pull the door shut? Okay, this is what I would like you to write down. There's a couple things that I want you to know about these relationships. So we're going to make this nice and clean. On a 45, 45, 90, the legs are the same. Those are always the same. And if you want to go from a leg to a hypotenuse, you times by radical 2, because it's got to get bigger to get as big as the hypotenuse. If you've got the hypotenuse and you want to go backwards and you want to find a leg, then you do the exact opposite. You're going to divide by radical 2. Again, the only one that has a radical 3 in it is the triangle that has a 3 in the name. It's not this one. Okay? If you've got a 30, 60, 90, everything goes through the short leg, and it's the only one that has a 3 in the relationship anywhere. So if we've got the short leg, we times by 2 to get to the hypotenuse. We divide by 2 to get to the short leg. If we've got the short leg and we want to go to the long leg, we times by radical 3. And if we want to go the other way, we divide by radical 3. What does that mean?
Mind blown.
Okay. You're going to be really, really thankful you got these just down cold. It'll take a little while, but you'll get there. Okay. Those are important relationships. Everybody got them written down? Okay, now, we use these particular triangles all the time. What we did is we just made sure that the hypotenuse is 1, and you'll see why we use this over the next couple of days. So what that means is I would take this and I would divide by radical 2. So off to the side here, I'm going to do 1 over radical 2, and then I'm going to think, hey, wait a minute. We did that in the warm-up. Rationalize the denominator, that's radical 2 over 2. And we might think, my gosh, I'm only halfway done, but remember, these two are always the same, so this is radical 2 over 2. This one's easy. If you want to go from the hypotenuse to the short leg, remember the short leg is always across from the 30-degree angle. It's exactly half. So this is 1/2. Piece of cake. Then to go from the short leg to the long leg, that's the one where we times by radical 3, so we end up with radical 3 over 2. So I'm going to shrink this down just a little bit, and I'm going to make sure everybody's clear on what these little sentences say at the bottom. You need to know these relationships. They come up a ton. So it's better off if you just know them. These numbers right here, you're going to want to memorize. Radical 2 over 2, radical 2 over 2 on a 45, 45, 90. On a 30, 60, 90, the short one is 1/2, the long one is radical 3 over 2. Those you're going to want to commit to memory. It would be better if you understood why they are what they are and stuff like that, and how we went from, hey, a 1 here, 1 over radical 2, rationalized and all that sort of stuff. Same thing on the other one. It would be better if you knew those. Okay, everybody good? Sort of? Okay, let's take a look. Find the missing sides and write in simplified radical form. Holy cow, 45, 45, 90. That one's just the same. Go from the leg to the hypotenuse, times by radical 2. Piece of cake, right? What about this one? I'm going to let Wilson answer. I've got the hypotenuse. I need a leg on a 45, 45, 90.
8 over radical 2.
8 over radical 2. Let somebody else take over. Keely, what are we going to do with this? Very good. We're going to rationalize the denominator. So this is going to be 8 radical 2 over 2. I'm going to simplify here. So I end up with 4 radical 2. I'm going to ask Angela, do I have a ton more work to find that other side, or do I have a little bit of work to find that other side? Why? How do we know the other side? It's exactly the same. Okay, so I got my answers right there. Goes pretty quick, right?
Yes.
Yeah.
Megan, this looks awful. How do I go from a hypotenuse to a leg of a 45, 45, 90?
Well, you just divided the radical 2.
You do, and what happens here? What's cool?
Cancel.
Cancels out, so what's here? 4. What's over here?
4.
Done. Okay, now, if that's easy, I just want to make a point, so please bear with me while we make a point. This stuff was discovered over hundreds, if not thousands of years. This is pretty amazing. Watch this. Using the sides of each triangle above, simplify the results. What do you notice? So the sine of 45. So I'm going to write down the sine of 45 degrees. Sine of 45 would be the 3 over, let's see, that's the opposite. The hypotenuse is 3 radical 2. I can cancel those. I get 1 over radical 2, which I'm going to write as radical 2 over 2.
No way.
Yes? Am I doing anything amazing there? Okay, so would everybody agree that the sine of 45 degrees is radical 2 over 2? Sine of 45 is radical 2 over 2. Now I'm going to change colors. Watch. Let's do this one. Sine of 45 degrees. Opposite. 4 radical 2 over the adjacent 8, sorry, over the hypotenuse 8. Simplify those. I get radical 2 over 2. Let's see. I was zoning out there for just a second. Did I get this right?
Yeah.
Sine of 45 is radical 2 over 2. Let's do the last one. Okay, I'm going to change colors. Keely, I'm going to write sine of 45 degrees on this one up here. What's the opposite side? 4. What's the hypotenuse? 4 radical 2. What can I do with this? Which is 1 over radical 2. And then what do I do with that? And what do I get? Okay. Everybody good? Okay, now, do me a favor. Type into your calculator radical 2 over 2. What'd you get? 0.707 something? Okay, type sine 45 into your calculator. Make sure you're in degree mode.
Sine inverse 45.
No, just sine of 45. What'd you get?
Same exact thingy.
1, 0, 6, 7, 8, 1.
Oh my god.
That's crazy.
It's there, isn't it?
What the?
Sine of 45 is exactly the same for every single triangle on the planet. Okay, so let's come down and take a look at this. Now, I'm going to try and speed this up just a little bit, a tad. This is find the missing sides, leave the answers in simplified radical form. So, be careful. 24, 30, 60, 90. You got to look at it and you got to think, wait a minute. Short legs over here. 12, 12 radical 3. Ooh, let's see. This is 30 up here. So this is the short leg. So if I double it, I can get the hypotenuse, 64. If I times it by radical 3, I can get the long leg, so 32 radical 3. Would you do the last two, please? Go. Go.
Wait.
Shh. done? Does anybody need more time? Okay. Did you get these? Did I do it right? We good there? Okay, now, I'm not going to do every one of these, but I want you to take a look. Let's just randomly pick some. I'm going to do the first one, okay? So the first one, the sine of 30 degrees would be 12 over hypotenuse 24, so we get 1/2, correct? Okay, Dane, tune in. Pick another one. Blue, green, black. What do you want? We're going with green. We're going with green right here. So we want sine of 30 degrees. Sine of 30 degrees. 30 degrees would be right here, yes?
Yeah.
Okay, I'm going to keep Dane awake here. Dane, what two sides are involved in the sine ratio? Say opposite.
Opposite over hypotenuse.
Opposite over hypotenuse. 11 over 22. Did we get 1/2 again? We did. And just for the heck of it, we'll do the last one because it's the ugliest. This is going to be the opposite, which is 16 radical 3 over 3 divided by the hypotenuse, which is 32 radical 3 over 3. Complex fraction, I'm going to flip this over. This is going to be a 3 on the top and a 32 radical 3 on the bottom. 3's cancel, radical 3's cancel, and 16 over 32 is 1/2. Did we get it right? And guess what?
45,000. Crazy.
There it is right there, okay? Now, we did this for sine of 45 and sine of 30. You could do it with every other trig function on there. You could do it with cosine and the other angles and stuff like that. Okay, have I made the point? Okay, slide down here. Thank you very much. Now, would you put a big fat star by this? I'm going to bold it, and I'm going to put a star by it, and here's the deal. This is what's going to get us ready for what we're going to do over the next couple of days. And this is what makes trig really useful. There's right triangle trigonometry that only works with right triangles. But just like when you learn about positive numbers, there are negative numbers. There are things that make the numbers much more useful. The same thing is true with trigonometry. So, trigonometry becomes extremely useful when you can apply it to angles greater than 90 degrees and to the xy plane. So here's the deal. We're just going to draw a reference triangle and find the reference angle. So at 120 degrees, again, we go counterclockwise. So I'm going to go this way 120 degrees. My terminal side would look like this, and I'm going to drop a line straight to the x-axis. That's this right here. That means the reference angle, listen carefully, the reference angle is always made with the terminal side and the x-axis. So look at this for just a second, and can somebody tell me what is the size, what is the measurement of the reference angle? It's this one right here. Somebody want to raise their hand and brave enough to say it? Wilson.
60.
It is. That's the reference triangle, and that's a 60-degree reference angle. So let's do the next one. 135 degrees. So we swing our angle open to 135 degrees. We draw our terminal side right here. We drop a line straight down to the x-axis. And I want to know what is the reference angle. This is the reference triangle. I want to know what the reference angle is. Oh, now Dane's awake. Dane, what is it?
45.
It is 45 degrees. If I do the same thing with 150, 150 would come all the way over here. Forgive my drawing. There's our reference triangle right here. Luke, you want to tell me what the reference angle is?
30.
It is 30 degrees. Would you draw the one for 210? You draw the one for 210. $90, 180. I got a couple degrees left over. There's the reference triangle. And I'm just going to call on somebody randomly. So Keely, what's the reference angle? What's this little cute angle right here? Well, if this is 180 to right here, and we've got 210 altogether, what's left for this little sliver of an angle? Say 30 degrees. 30 degrees. Very good. It's 30 degrees. Raise your hand if you got 30 degrees.
Upside down.
Okay. 315. 90. 180. 270 around to here. You agree 315 is going to be in here somewhere? So draw a reference triangle, and I want you to figure out what that angle is right there. Anybody got it? Keely? It is. It's 45 degrees. That's a 45-degree reference triangle. And I'm going to do 330. 330 stops just 30 degrees short of going around full circle. So this must be a 30-degree reference angle right there. Now, are there any questions about those? Yeah.
What if you do it with a really ugly angle?
You can do the same thing. Well, we won't complicate things right now, but you can do the same thing. So it says, now assume the terminal side of the angle is 1 unit long and use the reference triangle to drawn above to find these guys right here. So this is what I'm hoping we can do in the next couple of minutes. So I'm going to take this, and everybody follow along. This triangle has a side of 1. They told us it was 1. If that's a 60-degree angle, this is the short side, so this would be 1/2. This is the long side, so this would be radical 3/2. Now, do not make a gigantic deal of this, but we're on the xy axis, are we not? We went to the left, didn't we? So this should be negative. If we're talking coordinates on the xy plane, we went left 1/2, and then we went up radical 3/2. You good with that? Okay. The sine ratio should be the opposite, which is radical 3/2 divided by the hypotenuse. What's the hypotenuse? 1. So the answer should be radical 3/2. Would you put a box around that for just a second? If this is 1, remember we did this up above. This is radical 2/2, and this is radical 2/2. I almost have this perfectly correct. I'm missing something on it. What am I missing? Yes? This should be negative, right? So the tangent of 135 should be the opposite. Radical 2/2 over negative radical 2/2. And can somebody raise their hand and tell us what that is? It's not hard. D?
1.
What kind of 1?
Negative.
-1. Perfect.
I would raise my hand.
Okay, now this last one here, this would be radical 3/2, and this would be negative 1/2. Would you look at that triangle and would you figure out what's the cosine of 330 degrees? And we have just enough time to hopefully blow everybody's mind. Would you find out what the cosine of 330 degrees is?
It's this.
Hold on. Hold on. Don't give it away.
Oh, is that the thing that's supposed to blow our minds?
Okay, got that one. And 330 degrees. Cosine would be, that's the adjacent, radical 3/2 divided by the hypotenuse, which is 1. So that's going to be radical 3/2, correct?
Yep.
Okay. So same number, right? Which is about 0.86. Am I right? Okay, grab your calculator. Would you type in the sine of 120? Did we get it?
Yeah.
Okay.
Yes, sir.
Tangent of 135? Did we get it?
Yeah.
Cosine of 330. Now, of those trig functions, are any of them in quadrant 1? Hold on. Are any in quadrant 1? No. So can you use this? Whoops. Can you use this?
Nah. Well,
You
you'd
can,
have to
you can, but you'd have to make some adjustments to it. So here's what I want you to do.
but you're supposed to
This worksheet is not very long. Okay, I think you'll find some of them ridiculously quick and easy. Most of what we did is we did some thinking, getting some ideas in our head. Have that done tomorrow at the beginning of class. I think you're going to like tomorrow's notes. You're really going to like tomorrow's assignment. Okay? All right, good luck.